All right. Welcome to the fourth lecture in the RQI mini course or this course about quantum information protocols in quantum field theory. So right, hopefully you can see my screen. And hopefully you can still see me as well. Let me know about that. Cool. So I guess so far, what we talked about was about probes that would couple to quantum fields, and we spent the second lecture essentially seeing what we could do with one probe and seeing what would happen if we coupled locally to a quantum field, for locally in both space and in time to a quantum field. We found that we would see vacuum noise, we would basically see these virtual particles if we interacted for a finite time. We saw that we could probe the temperature of a quantum field theory, and that we briefly applied this to the Andrew effect. Then in the third lecture, basically after that, we started to play with two probes, and we coupled to the field. And we saw basically how the probes could exchange entanglement through the field, how the probes could basically be used to communicate through the field. Okay. The last thing that we saw in the end of last lecture was how, if you consider two gapless detectors interacting with the field, they could become entangled after a while, right? They would exchange information through the field, and they could become entangled if they were interacting for a time which is sufficiently long. So basically, what we saw last time was that two detectors can become entangled if they have enough time to exchange information through the field. So basically, the space-time scenario that we described last time, it was, well, having two detectors that would interact in regions that are mostly time-like. So the time that it takes for the interaction to take place is much longer than the size of each one of these detectors. And then these detectors would be close enough compared to their size so that they would be able to exchange information with each other. And this exchange of information basically would allow the detectors to become entangled. Okay, so this is what we saw last time. Now, what we will talk about today is something called entanglement harvesting. In entanglement harvesting, our idea is to not let the detectors communicate. So the idea would be to consider something that looks a little bit more like this. Oops. That looks a little bit more like this, where the detectors are separated by, they're space-like separated. So they're causally disconnected. They cannot signal to each other. But still, we're going to see that these detectors will be allowed to become entangled. So now we will study this. However, there's a series of conditions that have to be met so that this happens. And we will discuss this a little bit. I would argue that this is one of the most famous currently protocol in relativistic quantum information. And it has never been verified in a laboratory. We have never seen two space-like separated probes become entangled. However, there are many people doing experiments right now that most likely will be completed within the next, let's say, 5 years, which will see the first experimental results in this direction. I'm not going to say they're going to be able to implement fully fledged entanglement harvesting and everything, but probably we will see some experiments in this direction in effective things. I'll mention a little bit about this later, but okay, cool. So today we'll talk about entanglement harvesting. I guess the way to introduce this, the way to start talking about this, is to mention that the vacuum of a QFT has correlations, but it's more than this. It has correlations between any two regions of spacetime. I'm going to put a little asterisk here because technically it depends on the spacetime. It depends a little bit on the quantum field theory, but for free theories, for free field theories and Minkowski spacetime, this is definitely the case. I don't know if Nick mentioned the Risch-Leader theorem. That is basically one way of saying this. But the point is that this is there's a true statement in free quantum field theory, and it's basically the reason behind entanglement harvesting. And the point here is that some of these regions actually contain entanglements. So there's entanglement between some of these two regions. However, it's very hard to quantify entanglement, right? We saw that for 2 qubits there's the negativity, but in general it's pretty hard to quantify entanglement. So basically, right now, that there's no way to properly quantify entanglement between two regions of spacetime, between two finite regions of spacetime. Okay, there's no faithful way of quantifying this entanglement, which actually work for mixed states and everything like that. So our idea here is to extract entanglement from the vacuum. So if the vacuum contains entanglement between two space-like separated regions, maybe we can couple to these space-time regions, and then we can extract entanglement from the vacuum, and then we can use this entanglement to basically quantify the vacuum entanglement, or the entanglement that the quantum field in the vacuum state has between these two regions. Okay, and in order to talk about this, we will have to talk. We will have to work perturbatively. So perturbatively, and we will see why. So we will see why later. But basically, there's a series of no-go theorems for entanglement harvesting, and basically, we have to the only way to treat this properly is to do this perturbatively. There are a couple other ways that are numerical using new techniques. I might mention that at some point, but basically the standard and simple way to talk about this protocol is to use the perturbative approach that we discussed before. Okay, so if we consider two detectors starting in the ground state, so basically the initial state of the whole detectors field system will look more or less like this. This is a quasi-free state, and this would be ground state of A, and this would be the ground state of B. Okay, so if you consider this, now we can do the whole calculation, which I'm not going to do in this case again. I'm just going to say that just going to state the result, but it's very similar to the first perturbative calculation that we did in the last class. So basically, if you compute the UI, which is the time order exponential of the integral of the interaction Hamiltonian. This interaction Hamiltonian is the lambda mu a tau a lambda ax field plus the same thing for B. Now if you compute this Dyson series, we're gonna get identity plus first order plus second order plus lambda to the 4. And if we compute the final state of the detector, which is the trace over the field of so the trace over the fields of the UI rho 0 UI dagger, this is the final state of both of the detectors. What this will be given by will be the rho 0d plus some lambda squared rho d of second order, rho d2, plus terms of order lambda to the 4. Okay, so this is what we found last time, basically, when we considered A to be in the excited and B to be in the ground state. In this case, starting both in the ground state, that's more, I guess, usual way of considering entanglement harvesting. You can also do it for excited ground, but in this case, I would argue it's more usual. If you perform this computation, what you're going to find will be a matrix which is usually written like this, due to conventions that were introduced in a paper that I'll write down later, and we're actually going to check the paper later. So, but it looks like this. M star, and the what happens here is that the Lij is the Wij minus plus that we had, and the M term is, of course, the lambda squared, and the M is minus lambda squared, the Gij, so the Feynman propagator integrated with respect to the spacetimes mirroring. Sorry, this is a minus. There we go. So basically it's you use the same phase, right? So but these are just mirrored by distributions, the Feynman propagator and the Weizmann function, right? Cool. So and then the question, and this is all general, right? This is all general. We want to specify the situation to be that situation where we have the interactions to be space-like separated, or approximately space-like separated. Definitely not allowed to signal too much to each other at the very least. But before doing this, let's just study the overall properties of this final state, and then we can see how specifying it, the case where the detectors are space-like separated makes a difference. Okay. So the question we want to ask is, can this state be entangled? Okay. And well, in order to do this, we're going to use the negativity. Negativity is the sum of the negative eigenvalues of the partial transpose of the operator, right? We briefly discussed this in the first lecture. So the idea is to compute the rho d partial transpose. I think I call the rho f there. Let me use rho d up here as well. But yeah, the negativity, well, we need to compute the partial transpose of this operator. So the partial transpose with respect to A, well, A or B is not going to make a difference, but well, okay, but you just transpose each one of the blocks, right, in the matrix. So basically, if you transpose this block here, nothing changes, because this is so each one of the 2x2 blocks has to be transposed. If you transpose that block there, nothing changes. And this other block here, you're gonna get the M star is here, and the LAB star is up there now. Here the M is here, the LAB is here. And again, here nothing changes. Okay. Now the question is, are there any eigenvalues of this density operator which can potentially be negative? or which are negative. Okay, and the eigenvalues that you're gonna find will be 1/2 1 minus LA minus LBB plus or minus the square root of 4 LAB squared plus 1 minus LAA minus LBB. And the other, so these are the two eigenvalues. Here's the plus or minus, so we have two eigenvalues. And the other one is LAA plus LBB plus or minus the square roots of 4 m squared plus LAA minus LBB. And then if you take a look at these eigenvalues, you will find that this here can only be negative to order lambda to the 4, but this here can be negative to order lambda squared. So it is possible that the two it is possible that the two detectors will end up entangled. This is not a surprise, right? This is not a surprise because we saw detectors getting entangled yesterday. The question is whether they can get entangled when they're space-like separated. But just to conclude the calculation, then the negativity of the state rho d, basically to second order in perturbation theory, will be the maximum between 0, which is the case where this is not negative, and the value of this negative, the negative eigenvalue is when you pick the minus sign here, basically, right? So this is when it can be negative. And sorry, I wrote a plus here. This should be yeah, this should be a minus. No, this should be a plus. Never mind. Okay, L A minus L B B squared minus the L A plus L B and 1/2 times all this. Nice. So this is enough to quantify the entanglement of these qubits. Of course, this is only to second order. So to order lambda to the 4, we wouldn't be able to use this. But remember that negativity is this faithful entanglement quantifier for 2 qubits. Okay, nice. So what many people say, and it's true, and then I'll say it too because it's a good way of seeing what's happening here, is that entanglement is a competition between two terms. And this between the noise that they compute is a detector and between the non-local correlations that the detectors acquire. So it's a competition between non-local correlations. So the M term and the local noise acquired by the detectors.
May I ask one question?
Yes, of course. Go ahead.
Yeah, LAB also looks to be a non-local term. Like LAB depends on the position of both detectors A and B. So does LAB
Yes.
contain information about entanglement?
Well,
Not
it can to fourth order. If you go to fourth order in perturbation theory, you'll see that this eigenvalue here you will acquire some other terms and things like this, and you would see that there would be some potential for the LAB term to contribute. To leading order, it's only the M term that will allow you to get entangled. But it's but in principle, like the LAB term can also provide your well, can also allow your detectors to be entangled, basically. Yeah. But
Okay,
not to
thanks.
second order, not to leading order. Yeah.
No, I'm saying like here in negativity calculation, it's M term is contributing up to lambda square. But if you can compute, let us say, mutual information, so in that only LAV contributes, and mutual information basically contains total correlation information, right?
Yeah. Let me just one thing. Give me 1 second. Let me just double check the expressions for the LAB. So for the eigenvalues. So because yeah. So this is one of them, and so hmm. So if you go to fourth order, which is the wait, I do think that the expression that I have there is it has an issue because yes, I didn't think that this reference that I have open here would have that. Sorry about that. All right, so don't trust the expression for the other eigenvalue too much.
Okay, okay.
I think I copied the second term wrong. I don't think that there is the one basically inside the second parenthesis. Well, sorry about that. Let me share screen
Okay, okay,
again.
thanks.
But yeah, you have a good point. I was also that struck me
Okay, thank.
let me put a question mark here on the not in the whole expression, but I think the question mark is here basically. Not really sure about this one because it's true that these two would cancel, and then you would only get left with the square root of the LAB, right? Which could be to second order. I'll check this, and in the next lecture I'll definitely bring the correct expression for this. But the fact that I can definitely say is that this is the expression for the other eigenvalue, and this is the only one that can be negative to order lambda squared. These two facts are definitely true. Yeah. But yeah, good
Okay.
catch. This is a yeah.
Mm.
Cool. So now if LEA is LBB, then this very annoying expression can actually be simplified because we find that the negativity of the state rho with the maximum between 0 and m minus that, right? So if the two are the same, then this term here cancels. This term here becomes L with the factor of 1/2 that's there, and that's what you're getting it. So way simpler. Way simpler also to see that entanglement will be this competition between the non-local M term and the local vacuum terms, right? And here remember that these LAA and LBB are basically the vacuum excitation probability, right? Which can be sent to which decreases if the detectors are switched on for a very long time. But the key thing is that although it decreases if the detectors are switched on for a very long time, if we want to minimize the vacuum noise and we want to keep them space-like separated, we'd also have to increase the distance between the detectors. But if we increase the distance, then all of the terms decay, including the harvesting term. So there are lots of parameters to be explored here, and we're going to briefly discuss how it's possible to make these works. Okay. But before this, let me just let's do a very it's something that I've been saying it, but let's turn it into a more formal kind of discussion, which basically is the two ways for detectors to be entangled. So two ways for detectors to be entangled. one of them is what we saw last time, which is communication, right? And the other one is entanglement harvesting, in the sense that then the detectors will be extracting correlations from the vacuum. Nice. So, yeah, okay. So this M term, which is the only term that the leading order can give us the entanglement. It is this mirrored Feynman propagator with the lambda A and lambda B effects. Okay. And then we have here the Feynman propagator. Now, remember that this Feynman propagator, it has a real and an imaginary part. And this is important because each one of these parts is supported in different places. So then there is the delta of x and x prime, and this delta is the retarded plus advanced Green's function. So basically, if I fix the point x prime, oops, if I fix the point x prime, the support of delta is only going to be in the future and in the past of this point x prime. Oops. So these are the two regions where these are the two, what's kind of disappearing, but these are the two regions where the support of delta is non-zero, right? It's only in the causal past and causal future of the point x prime, okay? However, the Hadamard term, the h of x prime, is supported everywhere, absolutely everywhere in space-time. So basically, this is non-zero in space-like separation. The delta is not non-zero in space-like separation. Okay, so basically the idea is whenever we have the interaction of the detectors with the field, we can always think of this M term as being one half the Hadamard propagator with HA plus and lambda A plus and lambda B minus, which are the spacetimes mirrors of each detector, plus this delta contracted with each one of them. And now this is basically the splitting, which some people call M plus and M minus or something like this. We're not going to use this nomenclature here, but basically the idea is that, well, I mean, I already used it, but I'm going to stop using it very soon. But the idea is that this is entanglement harvested from the field, and this is entanglement due to communication.
So this is zero because of micro causality and especially separated results, right?
I'm sorry, could you repeat that?
And the second term is zero because of micro causality or especially separated points events.
Kind of. Remember that this is the Feynman propagator, right? This is not the basically there's a time ordering going on top of the commutation of the field. But yes, basically yes. If you go back to the first lectures or something like that, the idea is that the Feynman propagator, it is the time ordered version of the Whiteman function plus theta of t prime minus t w of x prime x. And of course, the Whiteman function is the one which is the expected value of the product of the field with itself, which is the 1/2 the expected value of the anticommutator of the field, plus 1/2 the expected value of the commutator of the field. And this term here is the one that's going to give you the retarded and the advanced Green's function with different signs, with different things. But basically, if you switch them, yeah. So the idea here is like this is I times the difference. So yes, the due to microcausality or due to the postulate, the definition of the suffering, because the commutator is the Green's functions, then this means that the inner part of the Whiteman function and of the Feynman propagator can only be supported within the causal future and causal past, right? And also notice here that this is the only state-dependent term. This term here, the commutator, is that times the identity, which means that every state, like, it is the same for every state of the field. So this is state independence.
So this state is independent for free fields.
I'm sorry?
So this is state independent for free fields, right?
The state independent part is the part that's going to be responsible for the communication, because again, it's independent of the states. It depends on what the detectors dump into the field, right? So here the detectors put the information. Sorry, put H here. This is delta. So the detector's information somehow is encoded into this into their spacetimes mirroring functions, right? And and I put plus here, should be minus. Sorry about that. That's but yeah, whatever. The point here is that this state dependent part. Oh my god, sorry, everything is exploding here now. Jesus. Okay, there we go. So, but the point is that yeah, this is basically the delta term only depends on what the detectors dump into the field and the exchange information. And the H term is what the field used to be before, which depends on the state of the field. And then the detectors are basically probing that and acquiring whatever correlations the field had there before. Okay, this is basically the splitting and the difference between communication and harvesting. I have two papers to refer to that do this very, very well. So this is the first paper that discusses this difference. Oh, 11, my bad, it's not a 5. Should be it's not a 0, should be a 5. 5, 6, 1. So this one will definitely describe this properly. And there's another reference that uses this to compare this with an interaction which explicitly only depends on the explicit exchanges between the detectors and is completely independent of the quantum degrees of freedom of the field. Okay, cool. So, by the way, I didn't give a very important reference of entanglement harvesting. We're gonna open the paper later, but yeah, then I'll essentially discuss this and we'll talk about it. Cool. So basically, why do we want space-like separation, right? So if we want to talk about entanglement, which was previously there in the field, one way of ensuring this, so one way of only keeping or only keeping the terms associated with entanglement pre-existing in the QFT is to consider interactions such that the delta of the lambda A minus lambda B minus is equal to 0. Okay. So this happens if the support of lambda A and lambda B, so the interaction regions, are space-like separate. Okay, so this is why we're interested in this case. And I'll put a little asterisk here, which is that it doesn't really have to be precisely 0, right? You can have some overlap that is very, very, very small, so that this delta term basically becomes negligible compared to the H term. So they don't have to be completely space-like separated. What really matters is that the delta term is negligible compared to absolutely everything else that you care about. Okay. So yeah, so basically in this case, M will be entirely due to correlations in the quantum field theory. And yeah, cool. So this asterisk, I'm just gonna qualify it. This basically means that it's enough that delta evaluated at the lambda A and lambda B is much smaller than the H lambda A, lambda B minus the L term. So basically it has to be much smaller than the whatever else you have left. And in this case, this is enough for you to say that the entanglement came from the quantum field and not from the interaction between the detectors. Okay, cool. So what I'm gonna do now will be to show you a couple of examples of papers that have studied this. There are lots of plots to be had. There are lots of things to be considered here. So let me just show you a couple of examples of what happens when you actually consider a physical situation of like interaction regions and things like that. So, okay. This paper here, I would say that is the first paper that has really talked about entanglement harvesting with the more modern language that we use nowadays. It's a paper by Alejandro Pozas and by Eduardo Martin Martinez. They discuss many things that we have discussed. You can see many hopefully familiar things, such as the Dyson expansion, the detectors, and then the initial state for the detector and for the detectors and for the field. You're going to trace over the field. So all of this is basically the language that we're currently using. This here is the density matrix that I showed you today, starting with the detectors in the ground state, right? Okay, so and here they will study entanglement harvesting when the interaction regions are given by Gaussian, so it's a Gaussian in space. And this Gaussian in space also comes with a Gaussian in time, as we'll see very soon. So here, the Gaussian in time. Okay? So this is what we call the switching function, because switches the interaction on and off in Minkowski spacetime, and then there's a Gaussian smearing function. So basically, I guess that the plots that I want to show is this plot here, the one on the right. Okay. So this is considering two Gaussian detectors in Minkowski space. The idea is that this d is the distance between the centers of the interaction in a frame which is co-moving with the detectors, and the delta is the time delay. So this is basically a space-time diagram where the first interaction happens here in this region here, and the second interaction happens in another region whose center is another point in this plot here. But the idea is that you see that whenever the detectors are separated by are positioned one in the light cone of the other one, you're gonna see way more entanglements being acquired, because in this case they're gonna be allowed to communicate from one to the other. But if you place the detectors in space-like separation or in complete time-like separation, this for a massless field, but if you place a detector in each one of these places, you see that the correlations really decrease very, very quickly, right? So basically, whenever you consider the detectors to be light-like separated for a massless field, they will get entangled way more easily than they would if they were space-like separated, okay? In order to see what happens with space-like separation, I'll pick this paper here that I co-authored in the past, but I think it's pretty the idea is fairly simple. So these are the coupling regions of the detectors that are considered, again, Gaussians, right? Separated by a distance L, basically, which is the scale of this, or well, yeah. Then using this setup here, you can compute up to which extent the detectors can become entangled, right? And the plot that is kind of the standard plot that you will see whenever you ask this kind of question. So the two detectors separated by a fixed distance L, space-like separated, and now you vary the energy gap of your detector. So this omega here is the energy gap, okay? And then you see that if the energy gap is too low, the detectors are not going to be able to become entangled. Then after some threshold for the energy gap, the detectors will become entangled. But now if the energy gap increases too much, then the detectors start being less entangled than they would be with basically this optimal energy gap compared to the mass, okay? So mu here is the mass of the field, okay? The mass of the field. So basically they're optimal parameters for you to attempt to extract this entanglement that is previously existing in the quantum field theory. And the energy gap is very important, because if it's too low, you're not going to see any entanglement. And if it's too large, you might either not see any entanglement, or you will see way less entanglement than you could by picking an optimal quotation marks energy gap. Okay, but this is the plot that most entanglement harvesting papers, most papers that study this in other setups, because this doesn't have to be done in Minkowski spacetime, right? All of the formulas basically applies for any other setup, any other space term for any other pair of detectors, and for any other Gaussian zero mean state of the quantum field, right? And this it's basically the structure of the plot as you vary the energy gap. The rest of the things are basically that I think we have some other plots here. I guess that as the mass of the quantum field increases, the entanglement will also decrease. This is not surprising. The correlations of the detector decay exponentially with the mass. So just, yeah. And something else that you will usually see in other papers, maybe. Okay, no, there's a different story. Will be that of course, if you increase the distance, the separation between the detectors, you also see the entanglement decreasing, because the correlation is decreased with their separation as well. So, but basically the idea is that so if I were to a sketch of what you will see in the quotation marks real world is that the the negativity behaves as this is a variable. it behaves as this. Okay, and this is a pretty general feature, and this is for the case where the detectors are space-like separate. Okay, for this setup here. Okay, cool. At best, or you're not going to see any entanglements, depending on the setup and the configuration and things like this. Okay, but there will be a peak. So basically, no entanglements for omega equals 0, and small or no entanglement for omega much larger than, well, the other scales. So very big. Cool. So this is basically what we expect to see. Yeah, any questions, any comments about this idea? Is it okay to get to space-like separated things entangled? Is that okay? Or does anyone want to, I don't know. When I first heard about entanglement harvesting, I thought that this would somehow violate causality for some reason. Because, well, they're space-like separated, how can they become entangled after this, right? But correlation does not imply causation. As a matter of fact, let me just comment this real quick, because this is something interesting to pay attention at. The reduced state of A is going to be given by adding the small parts of the matrices, right? So the row A will be the trace over B of the row of the detector. So basically, just add together you trace each one of the individual components. And what you're going to find will be, well, will cancel. So we already saw this before, but in this case, I think it's worth mentioning this again. So again, if Alice interacts with the field, she only sees her vacuum noise, right? And this is exactly what happens. So this means that Alice would not be able to tell whether Bob coupled to the field or not, but she could be entangled to the field. So entanglement doesn't violate causality in this sense, since you can get space-like separated systems entangled without violating causality in any way, right? Alice doesn't have any idea that she's entangled to Bob, and the only way to find out whether she is or not is to later compare the results of her experiments with Bob's, and then she'll say, oh, wow, whenever I measured up, there was a slightly higher probability that you would measure up, and yeah, you can compare this with quantum. Cool. So let's go back here to this plot. Let's briefly comment on this idea of the no entanglement for omega equals 0. Okay. Okay. So no omega for entanglement for omega equals 0. This, as it turns out, is a general feature of entanglement harvesting. It's a general feature of space-like separated interactions with a quantum field. So basically, this brings us to the no-go theorems of entanglement harvesting. So the situations where it's proven that you cannot harvest entanglements. Okay. These no-go theorems were mostly formulated by Eduardo Martinez and collaborators, but I would say that he is one of the things that made him famous, quotation marks. The two main references are arXiv 1703 02983 and 1803 11 214. Okay, so in order to discuss the de Noble theorems of entanglement harvesting, first let's briefly recall the entanglement breaking channels that I mentioned briefly in the first lecture, but we didn't really have too much time for that. So let's just entanglement breaking channels. So these are channels. So phi is entanglement breaking if whatever you do to one of the sides of the channel, to one of the sides of your system, if you apply phi to the other, this is always separable. No matter if gamma has entanglement, whatever, if you apply this identity tensor phi, you just apply phi to one side, and now your system is not entangled with anything else. Okay? Now, a channel, so phi, and of course, like being separable means that it's a non-entangled state. Okay? So phi is entanglement breaking if and only if you can write phi of rho as being a sum over k. This for finite dimensional systems, but it generalizes for infinite dimensional systems with no issues whatsoever. But basically, if you can write phi, if you can write your channel like this. So basically, if phi only depends on your density matrix through expected values. Okay? And there is this concept of simply generated unitaries. So simply generated unitary is a unitary which is e to the minus I mu tensor x. Okay. So in this context here, mu is an observable in system A, and x is an observable in system S, another system. Okay, cool. So now, if you were to compute rho A, which is the trace over S of applying this unitary to say that A and S start in a separable state, and you apply this unitary after, now you're going to see that this will be the trace over S of this e to the minus I mu x rho 0 A, rho 0 S, e to the I mu tensor x. I see the tensor here. Cool. But now this trace over S, we can just add we can just take this trace over the eigenbasis of x. So if x is an observable, we pick the eigenbasis of it. So this is actually going to become a sum over these xk's, rho 0 A, rho 0 S, into the I mu x. Oh, this is not a parenthesis, this is the cat. But now, because xk is an eigenvector of x, I can just put it through and replace the operator by the eigenvalue. So we get e to the minus I mu xk rho 0 A Then we're gonna get oops. Yeah. Then the xk will okay, 1 second. Let me just restart the screen share for it. So okay. So and like here. Share screen. There you go. So all right. So going back here. Right. So now we're gonna have yes. So we're gonna have this. The xk is gonna hit the row 0s. The next k is gonna hit the row 0x here, and this is gonna be an I to the I mu xk. So what we see here is that we get these expected values of the row 0s, and then we get these operators of rank simply generated unitaries applied to the row 0a. And this generalizes to, so this generalizes to continuous spectrum. Continuous spectrum. But basically the idea here is that you can put this in a form such that the row 0a is not going to be such that this will be entanglement breaking. Okay. And so this implies two things. The first thing is you remember that when we computed the well, we're gonna go through this again, but the first thing is that the delta coupled detectors, they cannot entangle they cannot entangle, period. The reason for this is that for two delta coupled detectors, we have that the unitary will be the time ordered exponential e to the minus I, the integral dv hi of x. So this hi of x, let's write this fully as a time ordered exponential of minus I, the integral dv. You're gonna have a lambda. This integral dv will actually become a the integral d3x. Let's place the times. So let's do this carefully. So delta coupled means that we have two detectors, and they will interact here and say here. Okay. This basically means that the spacetimes varying function is a delta of tau minus tau 0 times fa of x, and this one here is, let's say, tau minus tau a, and this is the delta of tau minus tau b times fb of x. Okay. Now, in this case, if you have these detectors there, and you need to compute the time ordered exponential of minus I, the integral dv of mu a of tau a lambda a of x phi of x plus mu b of tau b lambda b of x phi of x. If you need to compute this, now this time ordering is basically going to pick whoever happens first, or if the interactions are space-like separated, that field operators commute. So, and the mu operators commute as well. So basically, this will always factor as a UA, so as UA, where this is simply the e to the minus I mu b phi of lambda b will be at the at the time where b interacts phi of lambda b, and e to the minus I mu a at the time where a interacts phi of lambda a. Okay. And because of this, you're just applying a simple unitary in one, and then a simply generated unitary in the other. So each one of these entanglement breaking, so you're never going to be able to get the two detectors entangled. So can never entangle two delta coupled detectors. There's some caveats here. So if you start having multiple delta coupled interactions, then of course you can interact the detectors. In fact, you should be able to approximate any interaction by a bunch of delta coupled detectors. There's actually a recent paper in the archive that does exactly that. So of course, if you start considering multiple delta interactions, then you can start getting the detectors entangled, but only with one here, one there. The detectors are never going to be entangled. Then these arguments also partially applies to gapless detectors. Because remember that for gapless detectors, we could kind of factor the unitaries like that, but we got an extra term. We got an extra term when we're getting these, and also like basically this argument applies to gapless detectors only. So this only applies if the interactions can be separated by a Cauchy surface. Cauchy surface. So basically, if you can pick a notion of time, doesn't have to be a Cauchy surface, just locally is enough. But well, the point here is that if you can define a notion of time such that the interaction of A happens before the interaction of B in that notion of time, then you cannot find the finite entanglement between A and B. If you can't do this, then you might. And basically, the idea here is that before we had our U for the gapless case. If you remember, it was e to the minus I mu a. No time dependence at all in the mu a. Phi of lambda a minus I mu b phi of lambda b. Then we got another term, which was an I over 2 delta AB, basically, which was a phase times the mu a mu b. And now this unitary here, if you apply it over A, this is not a simply generated unitary because you have the mu b here. You have this term which can definitely entangle the two qubits. In fact, can even take it out of the exponential because it does commute with the other two. And it does commute with the other two, and you can simply get the detectors entangled regardless of the rest of the interaction, right? So notice that this term here, it will only be non-zero, again, if they are causally connected. So this is x prime, then you have the delta and the delta. So you need the interactions of A and B to be causally connected for this term to be non-zero, but also this term here, the sum of the two, and now it's not as trivial to separate them into two simply generated unitaries, right? Because so if the detectors commute, sure, if the space like if the regions lambda A and lambda B are space like separated, sure, you can just get rid of this. You can just separate them because then the fields commute. So let's check the two cases. So if lambda A and lambda B space like separate, then in this case delta AB is 0. And the commutator between the fields, between the field in the two regions, is also 0. So in this case, you can just, because the fields commute and the mu's commute, this implies that your unitary is just going to factor like this. Right? And e to the minus I mu b phi b. So no entanglement. Because now these are simply generated unitaries. Okay. So what else? The other case here is and of course, if I draw two little blobs like that are space like separated, A and B, then in this case you can always find Cauchy lies between them, right? No matter where I place them, right? So if I do these two, you cannot get them entangled. And sorry, these are not space like separated. This is another case. But if I draw two space separated, you can always fit them some space in this case. And the other thing is that better thing that applies here as well is in the case where the one interaction happens after the other one. Okay, in that case, I'm not going to do the calculation, but I'm just going to state here that if lambda A or lambda, say the lambda B is in the causal future, lambda B is in the causal future of lambda A, then then what's going to happen is that this delta AB that we have here, this term will be non-zero. So the delta AB will actually be the retarded propagation from A to B, which is the same as the advanced propagator from B to A. Same thing. So now we could argue, well, okay, so now we have this mu A, mu B. So it's possible for them to get entangled. But turns out that no, because in this case, when you try to write this unitary as two simply generated unitaries, you're going to pick up the field commutator. And the field commutator is going to cancel this term as well. Okay, so delta B is going to be this, which is definitely which potentially is non-zero. But when you write the unitary, and you want to write it as e to the I mu A phi A e to the I mu B minus mu B phi B. In order to do this, you gotta pick the price from the Baker Campbell-Hausdorff formula, right? And the price will be an e to the I divided by 2 e AB. Okay, and the EAB times mu A mu B. And this term is the retarded minus advance, right? So in this case, this term, the only term that will matter will be the advanced from A to B. And it will come with a minus sign that will kill the delta there. So we're gonna get a minus here. So these two terms will cancel. So in the end, yeah, these two terms will cancel, and you're gonna be left with terms that are zero. So in this case, the GR is zero. So also no entanglement. Cool. So basically, yeah. So the summary in picture is that whenever there is Cauchy slice between interaction regions, they cannot so gapless detectors cannot become entangled. And now if you want some examples, if you have A here and B here, they're not going to get entangled. A here and B here, not going to get entangled. A here and B here, they're not going to get entangled. So these are all cases where you can find Cauchy slices. This last one was barely a Cauchy slice, but whoop. So so no entanglement. But there are other cases, such as the cases that the last lecture, where, for instance, one interaction region is very long and the other one is also very long. Or, for instance, if one of the interaction regions is very long and then the other one kind of, I don't know, if you have something like one of the interaction regions kind of like wraps itself around the other one or something, then in these cases, you can definitely can also get them entangled. Well, many other cases. So can become entangled. Because here you can't find a local notion of time evolution such that you can factor the unitary like this. Yeah, okay, cool. So this is basically the no-go theorem of the no-go theorem of the paper 2018 that I said there. And the final thing that I would like to say today, so today will be a little bit shorter, I guess, is that when the interaction between the detectors is entanglement breaking. So when you can't get them entangled, then it's possible to compute the classical channel capacity of the channel between them, right? So basically, if A interacts before B, then the channel capacity is given by the following. The have a function h, which is related to entropy and shows up a lot in information overall. That I'll define in a second. 2 lambda squared. I'm just gonna call this the LBB that we had from before. So minus 2 LBB divided by 2 cosine of 2 lambda squared delta of lambda A, lambda B, and minus h of 1/2 minus e to the minus 2, the LBB, which is the local noise term, divided by 2. And here, where h of h of x, just minus x log 2 of x minus 1 minus x log 2, 1 minus x, just like a binary entropy of binary channels. And in these cases, of course, because their entanglement breaking, we have that the quantum channel capacity is 0. And notice here that if they're space-like separated, then this coefficient here becomes 1. And sorry, this is a. Now I have a. Okay, give me 1 second so that I check the value of this, whether there's a plus sign or minus sign in both. I'm pretty sure that in both it is the same, because the classical channel capacity will be 0 if they are not causally connected. So yeah, 1 second. Let me just check whether it's a plus or a minus here, and I'll get back to you, and I'll write it properly there. That was my bad, because I had one with the plus and the other one with the second. So I guess that I copied it with the wrong sign here. So okay. It is a plus. Yes, it is a plus. Yeah. Okay. Cool. So, all right. It's the plus. So this expression is definitely correct. Cool. This is what I wanted to say for today regarding entanglement harvesting. What I'm gonna say is that yeah, there are a couple of other fund information protocols that you can implement using basically this formulas that we have been talking about here. I'm not going to have time to talk about them, but I'm just going to briefly mention quantum energy teleportation, very interesting, and also involves relativity and even general relativity. I mean, the idea is to use correlations in order to extract energy from the vacuum of a quantum field theory. But that is a protocol that would be hard to go in depth in one lecture, so I'm not really going to have the time to do this. I will most likely, most certainly, right here, just check quantum energy teleportation, and there are many papers by Masahiro Hotta regarding this. And the idea is to extract energy from the vacuum using correlations that are shared between local probes that come to the vacuum. So yeah, take a look at that. And then the plan for tomorrow is to handle everything that I have not talked about regarding the detectors. So basically, we will talk about how to relate them with physical systems that can couple to quantum field theories, and we will talk about what are the consequences of the fact that the description for the detector is non-relativistic. And we're also going to talk about how to describe wave functions in curved spacetimes briefly. So tomorrow will be a longer lecture than today, that's for sure. And our main goal for tomorrow will be to basically discuss a little bit more about the how to relate these detector models with more physical systems, such as atoms interacting with lights and things like this. Cool. So are there any questions or anything that anyone would like to get clarification on? for this lecture?
Excuse me, doctor. Just as a question about fundamental that you said in the first of the lecture, uh, between the two spaces about the past and future that you mentioned, uh, is it true that two spaces in the entanglement that information must be transferred? Two spaces must be the same, or can be different spaces. For example, uh, imagine that one of the spaces on the sitter and another one, yeah, in on this anti-de-sitter spaces. Is it possible or no when they are far away and in entanglement?
I'm going to say that I don't know how to describe things when you have more than one spacetime. You might have one spacetime that locally looks like the sitter and locally looks like anti the sitter in the same spacetime. And in that case, the only way to say whether there is entanglement there or not is, well, to actually do the calculations. You could try to couple systems there that try to harvest entanglement. You could try to use some other entanglement quantifiers applied to the quantum field theory. But this is all assuming that we have one background spacetime, which is the only case that I feel comfortable describing for now. So yeah, one spacetime that locally looks like something and locally looks like something else, definitely. Everything that we discussed here applies. The two spacetimes are things like this. This is too general.
Thank you very much.
No worries. Okay, cool. Okay, thank you so much for joining. I'll stop the recording.